So for our radioactive decay explore, what we're looking at is how material in rock can clue us into the age of the rock or the organism over time. So one of the things we talked about was this idea of a radioisotope, an unstable atom that can convert into a new material over time. So what we're looking at is the ratio of what we call parent isotope to daughter isotope as the rock ages. So this is a great place to start, this background information. Check it out. Just get a little background about this process. And what we're looking at here is creating our own set of data to use to really understand this idea. So in our lab, we are using coins to represent radioisotopes or material within a rock. Our heads is going to represent parent material. And so the parent material is the original radioactive substance. That's going to be heads. So this is material 1, or the original material. Our tails is representing something called daughter material. And daughter material, well, is representing the decayed material. Okay, the newly formed decayed substance. This is the stable material. So when we have a rock that's formed, so initial time 0, when that rock is formed, 100% of the material that it's made of is this parent material, the original radioactive substance. Over time, that substance decays into the daughter material, but in the very beginning, there isn't any of that. So as we work our data set here, we're going to see the total parent decrease and go down, and our total daughter will increase over time, all the while not changing total at all. So you're going to use this set of directions that we shared in class. And also on this slide. You might want to just screenshot it from the video so you can use it while you're doing the lab. But you are going to use 50 pennies, or any coin really, if you have them. You're just going to turn them over, and you're going to differentiate the number of heads, parent material, to tails, daughter material. And you're going to record those in step 1. Okay? So let's just say you end up, first of all, with like 10 daughters and 40 parent. Great. Your total is still 50. You still have 50 coins. The material in the rock is not going anywhere. You have 40 that stayed radioactive and 10 that decayed into this stable. This is going to stay as 10. Those are never changing. This 40 has the opportunity to continue to decay. So in your turn number 2, you're going to reshake these 40 coins and slowly, again, see this number decrease. Let's say my second one ended up with 35. So 35 heads. That means 5 new coins were turned to daughter material. So my total now is 15. This is what I want to have recorded. So again, this is going to increase as we go down the line. This is going to decrease as we go down, all the while totaling 50. None of those coins are ever going anywhere. So you're going to make that happen. If you don't have coins at home, there's a link right here to a generator website. It's just not as effective. It'd be great if you could use 50 coins, any coins. Once you have your data set, then you're creating 2 graphs. One line showing the parent material, and you can do that in blue, and one line showing the daughter material, you can do that in red. So in the table up here, this is our x-axis for both parent and daughter. And then, of course, this is the number we're going to use in blue, and this is the number we're going to use in red. So you're going to make your way across, turn 1, 2, 3, 4, and then 0, 10, all the way up to 50. So you're going to see both of those lines go across the graph. And then a few questions here, looking at the graph and kind of talking through the idea. There is one final calculation here, another example of decay of radioisotopes over time. This time, instead of doing pennies, we're using actual amounts, actual matter. So here it tells us the sample is starting with 80 grams. So if I have 80 grams to start with, I don't have any daughter yet. Looking at the half-life, the time it takes for half of the material to decay, we should see this decrease by half each time, and then the daughter adding it all together. Okay, one final big picture question. How might the age of rocks be a helpful evidence in figuring out how our plates move? So adding that new age evidence to our rocks and our fossils, what might new clues would we get having this age data? As always, message back if you have a question. Submit when you're completed.